Hello everyone, my name is Alex Kozachinskiy and this is my joint work with Natalia Dobrokhotova-Maikova and Vladimir Podolskii titled Constant Depth Sorting Networks. So our context is the problem of sorting in which we get an array of integers and we want to output these integers in the non-decreasing order. And there is a classical class of algorithms for this problem called comparison-based algorithms. These algorithms basically the only thing you can do with your integers is compare them. So I would say it's better to imagine that you have just n stones of different weights, and your task is to order these stones according to their weights. But you can't just tell by looking at them which one is heavier and which one is lighter. So you just have weights, and you can take any two stones and you can compare them. And then what you are minimizing is the number of comparisons you do. Now, sorting networks, again, is a very restricted subclass of the class of these comparison-based algorithms. In a way, sorting networks are non-adaptive comparison-based algorithms in which you kind of don't see the results of comparisons. Well, but then the question is, whether we can still do something in this model if you don't see the results of comparisons. Well, what's the model? Uh, Now, in the sorting networks, you can imagine that you have n stones that that go in the row. They lie in the row and on some table, let's say. So, like here on the left, we have four stones, and from bottom to the top, their weights are 4, 1, 3, 2. And in the end, we want them to go in the non-decreasing order with respect to their weights. So it has to be 1, 2, 3, 4, like on the right here. Now, what you can do, just the only thing you can do at one step is to indicate a pair of positions and ask an oracle to swap these two stones in these positions if they go in the wrong order. Like, I don't know, like 4 and 1 here on the left. They go in the wrong order, and if you ask an oracle to swap them, then in the result you will have 1, 4, like in the next row. Okay, but the point is that oracle doesn't tell you whether he really swapped these numbers or whether they actually were okay. They were in the right order. And so what you can do, you just, in this model, you can just indicate a sequence of pairs of positions, and just Oracle performs these swaps if necessary. Uh, and still, in the end, this sequence of pairs of positions, which is a sorting network, should always correctly sort all possible inputs of integers. And so here is an example. What we do in this example. So on the left, we have, let's say, some initial array, some initial row of stones, some initial array. What we do is just we ask to swap the first two arrays and then the second two stones, and then the first two stones, and then the third and the fourth stone. Okay, and then what we do on the next step, we kind of take, so we did two swaps. So now we know that the second stone is the largest one among the first and the second position. And the fourth stone is the largest one in the third and in the fourth position. So now we take the second and the fourth position. So we kind of take two stones that were heavier in their comparisons, and we take two lighter stones and compare them. And after that, so we already did four swaps. After that, we just know that the fourth position now contains like the heaviest of the heaviests, and hence in the fourth position we have the largest stone, and the first position now has the lightest of the lightests. And again, this means that in the first position we have the right stone, the minimal weight stone. But again, we don't really know what happens on the second and the third position, and if we do just one more swap, so which um, fixes the situation if it has to be fixed. So this is a sorting network with 5 swaps, but notice that it's also organized in levels because initially, well, I can ask to swap a pair of positions, but imagine, but if they are like disjoint, like on the first 2 swaps, then I can actually imagine that I do this all at once. And this defines another very important parameter of sorting networks called depth, which is, of course, of interest if you want to parallelize the execution of the sorting network. And the depth is just imagine that at one step you can do an arbitrary set of swaps, of disjoint swaps. And then the number of such steps, where in one step you can do at most n over 2 swaps, but they has to be disjoint, is the depth. So here the depth is 3. We do this algorithm in 3 steps, but we do 5 swaps. So sorting networks are studied since 1950s. It's quite an old topic, and one of the main interests in sorting networks is because they are just made for hardware. This is a kind of algorithms where you don't have any conditional operators, right? So you don't you have just a fixed sequence of commands, and you just do them regardless of what happened previously. And still, there are important problems in this area. But first, let's give just a slight overview what is known about them. Well, we will be mostly interested in the depth. Well, because let's say if we have depth d, then we know that we do at most d times n over 2 swaps. Because at one step we can do at most n over 2 disjoint swaps. And since sorting networks are still comparison-based algorithms, there is a standard information theoretical lower bound which says that the number of swaps has to be at least binary log of n factorial, which is 1 plus small of 1 and binary log of n. And this automatically means that depth should be at least logarithmic in the number of integers you want to sort. And most specifically, it has to be more or less at least 2 binary log of n. Well, 2 plus small o of n, small o of 1. Now, and on the other hand, if we would have a construction where the d is logarithmic in n, we would automatically obtain, this would be a construction where the number of small swaps is also asymptotically optimal. Now, unfortunately, the situation is kind of like this. There are many relatively simple constructions where the depth is log squared n. And so it gives the number of swaps n log squared n, which is close to optimal, but not optimal. And there is only one construction where depth is actually logarithmic due to Achtai, Conlos, and Semireni. But there are some important drawbacks of these constructions. Because the argument and the constructions are very complicated, and it should be very hard to implement this in hardware. And the other problem is that the constant before log n is quite large. It's of order 1000 or something. And in order for this construction to outperform, all these standard constructions where depth is log squared n, but the constant is somewhat 2 or something like that, or even 1, n has to be really, really huge. So the noble problem here is to come up with try to search a simple construction or simple argument where depth is still logarithmic and hopefully the constant is not that large. Now, in terms of constant before log n, so we know that it isn't, there is some optimal constant. We know, as I already said, this is at least 2, but there are some improvements of this um, simple information theoretical argument. With the current best known is 3.27 log n, and the upper bound of Achtai-Common similarity is far away from this 3.27. Partly motivated by these questions, we study the following generalization of sorting networks called K-sorting networks. So ordinary sorting networks are two sorting networks, but in general, in K-sorting networks, what you can do at the unit cost, you can indicate K positions in the array, and then you can ask the oracle to order integers in these positions in the non-decreasing order, but without touching any other positions of the array. So instead, in ordinary sorting networks, we just do this, but for pairs of positions. And now we can do this for any k tuple of positions. Now, in this example, this is more or less actually the same example as we had before, but now we have 8 inputs, and now k is 4. So in the first step, we in the first layer of our network, we take the first 4 positions and the second 4 positions, and independently we ask the oracle to order them. Now on the second layer, what we do, we take the best, well, like the heaviest 2 stones in the first 2, in the first 4, and the heaviest 2 stones in the second 4. And we ask to order them again. And the same, so we take best of the best and worst of the worst. So after that, we know that the first and the second, in the first and the second array position of the array, you will have two the most light stones. And in the seventh, in the eighth position, you will have the heaviest and the next to the heaviest stone, right? Because these two were winners of the winners, and the first two were losers of the losers. And again, once again, we don't know what happens in the middle 4 positions, so we do one more call to the oracle, which sorts the middle 4 stones. Okay, so what do we know about this model? Let's start with something simple and understand that the depth now should be at least log n base k. Why is that? Well, because if you consider just one layer of your network, in one layer you just partition your inputs into the positions in the array into tuples of size k, and you order your array inside these tuples. And then every output of one layer depends on at most k positions in the previous before the layer. Now, if you have d layers, every output of the network depends on at most k to the d initial positions in the array. Now, but obviously, if the network sorts all inputs correctly, then every output should depend on all n inputs. So from that, we deduce that d should be at least log n base k. And notice that when k is 2, we actually had a very simple argument showing something slightly better. We had 2 binary logs of n. And now obtaining not 1 but 2 is not that obvious, and then we will return to that. But what we know, what else we know? So now log n base k is a natural benchmark for d. And the situation kind of repeats the situation with k equals 2. Well, but now there is only one kind of simple construction where D is quadratic in log n base k due to Parker and Parbury. And it was also noticed by Chevatal that we can generalize the sorting network of H-type Cumulus and Semiredi to this setting of k sorting networks. So again, there is a simple construction with quadratic, which is quadratic in log n base k, and it complicated, and it has the same drawbacks as in case k equals 2 construction with just log n base k depth. Okay, so now what we are actually doing in this work, we are interested in the following question. Let's say I fix D. I say that D is some constant, let's say 3 or something. And then I study the following question. I know that I can use only 3 layers, say, of these K sorters. Then how large K should be if I want to sort n inputs? So this is our problem. And the motivation that I'll explain in a minute is that we can use such constructions where D is constant and hopefully K is not that large iteratively by applying it to its own elements to get eventually a probably good one, a good ordinary sorting network by recursion. Okay, let us discuss what we can achieve by recursion. Assume that we have a construction of a k sorting network for some constant depth d, and k, which we will call the arity of the network, being significantly smaller than the number of inputs. Let's say that it's n to the alpha for some alpha smaller than 1. So let's imagine that we have something like that. What we can do? Well, so it's a k sorting network, so it consists of d layers, and each layer consists of several disjoint k tuples that are being sorted on this level. And instead, now we can apply the same construction to each of these k tuple. And because the task is the same, we now have to sort k elements instead of n. And we know that we can do this with arity k to the alpha, right? And in n, it becomes just n to the alpha, so n to the alpha squared. And depth becomes d squared because we have d layers, and to simulate each layer, we need d more layers, and in total d squared. We can repeat it once again, and then we will have depth d cubed and arity n to the alpha cubed, and well, any number of times we can do that until the arity becomes 2. This happens for some t number of these recursive iterations, and the depth of the resulting, and this will be just an ordinary sorting network with k equals 2, and its depth will be small d to the t. And then we can express capital D from everything else by excluding t, because we know that it has to be such that n to the alpha to the t equals 2. And doing some calculation, we obtain that capital D, the depth of the resulting ordinary sorting network, will be log n to some exponent, and the exponent is something like log of d base 1 over alpha. And it would be great if this exponent, let's say, is smaller than 2 at least, because as we've been discussing, there are a lot of constructions where the exponent is 2 for ordinary sorting networks, but only one where it's just logarithmic in n and very complicated. And it would be fine if it would be nice if we would have some simple construction, and this idea of just recursively applying the circuit to itself is very simple. It would be nice if it would at least give us something better than square. Well, hopefully it might get something which is more or less close to optimal, but who knows? And to achieve at least something better than the square, you can see that we have that alpha should be smaller than 1 divided by square root of d. So finally, our results. So our problem again is that we fix d, and then we consider all sorting networks of depth d with n inputs, and we are interested in what is the minimal k, such that a k sorting network with such parameters exists, which if we fix d, it just becomes a function of k. And we obtain a precise answer for all d up to 4. So let's see what we have. So, well, first we can, for fun, consider the case d equals 1. And observe that obviously we cannot do anything than just k equals n, because every output should depend on every input. Now, it turns out that the same situation is for d equals 2. This is, even if you can have two layers, two steps of your algorithm, then you can not sort all n inputs. If you can, at unit cost, you can only sort smaller than n number. It's in two steps. So, but for d equals 3, the answer becomes smaller than n, and yet it is not as impressive because it's again some linear function in n. More specifically, the minimum is exactly n over 2 rounded up for every n. And finally, for d equals 4, the minimal k becomes sublinear. More specifically, it becomes of order n to the 2/3. Now, with regard to possible recursive constructions, these all results are negative. Let's see why. Because, well, at least for d equals 3, we see that k is linear in n. And in order to obtain something reasonable from a recursive construction, k had to be something like n to the alpha for some alpha smaller than 1. And if you try to do this with linear k, with n over 2 k, you will get eventually will get some sorting network of variety 2, but its depth will be even not it will be not polylogarithmic. Well, and now if you take d equals 4 and start to do this, you will get something polylogarithmic, but it actually will be worse than log squared n, because to obtain log squared n, as we saw on the previous slide, we have to have alpha 1 divided by square root of d, and if d is 4, it's 1/2, and here the minimal possible alpha is 2/3. So unfortunately, we don't get anything interesting from it. And finally, we also show a general lower bound for arbitrary d. We show that if we have a sorting network with a k sorting network depth d, so we basically show that k is at least n over 2 to the 1 divided by d over 2 rounded up. And also, I have to note here that the upper bound for d equals 4 was actually implicitly no. So our contribution here is the lower bound, the matching lower bound. And final remark is that the lower bound for arbitrary d is if you write it as a lower bound on d, you will obtain something. Before I described you a simple argument showing that d is at least log n base k, and here you can get 2 before log n. So we will discuss it a bit later. What's left open, of course, is whether there exists some constant d at which there exists a construction of a k sorting network, which after recursion gives us something better than log squared n at least. So in other words, we are asking whether there is construction with some fixed d, and k, which is n to the alpha for some alpha smaller than 1 over square root of d. And but beside that, it's also interesting to figure out what is the minimum k for large d. And we don't know the exact answer already for d equals 5. So what we know is that from our general lower bound that alpha is at least 1/3, but what we also know is that alpha is at most 2/3, but that's just an upper bound for d equals 4, which is also obviously an upper bound for d equals 5. The more layers you have, the easier it is for you. And let's say, and also a separate question for some, let's say whether you can achieve alpha at most, say, 0.44. Why this number? Just because 1 divided by square root of 5 is something 0.44 and something else. If you have 0.44, then you will obtain something better than log squared n after recursion. And just so and not, nobody knows actually, like it may happen at some random depth, let's say d equals 10, and just for d equals 10 you need something better than 1 divided by square root of 10, and that's, so for example, alpha 0.3 would work. And in the rest of the video I would like to present you our technique. But let us start with some notation. So we represent sorting networks as such diagrams where, well, remember that sorting networks have layers where on each layer we sort some disjoint k tuples of positions. And in our case, k is 4, and these tuples are given by colors. So let's say on the first layer, the first tuple which is sorted is the first 4 positions of the array. And this is given by the first 4 blue circles. And likewise, the second sorted tuple is the tuple of the last 4 positions, and this is given by red circles. And we also have these columns of square cells, and this is just the content of our array at different moments. So let's say the leftmost column is the content of our array at the very beginning, and we assume that the indices of the array go from the bottom to the top. And the second column, let's say, is the content of the array after the first layer of the network. So after we did the sortings in the k tuples in the first layer. And these square cells, we will refer to them, well, their position, to specify their position, there are 2 ways. So let's say consider the second column. Whenever convenient, we will say that these are cells after the first layer, and whenever possible, these are also cells before the second layer of the network. And for example, output cells, they are cells after the last layer. In this case, these are cells after the third layer. And what else I want to mention is that in our lower bounds, it will be sufficient for us to only consider arrays consisting of zeros and ones. And I just would like to mention that this is not strange because, in fact, there exists a classical 0-1 principle which says that as long as your sorting network correctly sorts all arrays consisting only of zeros and ones, it correctly sorts all arrays of arbitrary integer numbers. Now, our main technique is called access technique. So to define it, assume that we have a sorting network and we fix some input array X, which consists just of zeros and ones. And then we say that we have access to some cell of the network on input X if currently this cell contains 0, its value is 0, but we can change some of the input bits from 0 to 1 such that the value of this cell becomes 1. So on this example, X is written in the leftmost column. It's 0, 1, 0, 1, 0, 0, 1, 0. And for example, I'm claiming that I have access on this input to the following orange cell. And to see that actually this access is established by the following sequence of orange cells. First, the first observation is that I have access to all input cells in the leftmost column that are equal to 0 because I can change them to 1 without any restriction. So in particular, I have I have access to the orange cell on the bottom, on the top of the leftmost column. Now, in the first layer of my network, I have a red quadruple which sorts the last 4 input cells. And currently, in the last 4 input cells, I have just one bit which is equal to 1. And if I switch the orange cell to 1, now in the outputs of this red quadruple, I will have 2 ones. And because the outputs of the red quadruple should be ordered, it has to be this orange cell in the second column. Now, what happens in the second layer? In particular, in the second layer, I have a red quadruple which takes the 7th and the 8th cell, and also the 3rd and the 4th cell. Now, currently, in the current picture that we see now, in the inputs of this red quadruple, we have 3 ones, right, and 1 0. But if this orange cell changes to 1 in the second column, this means that the number of ones in this red quadruple in the second layer now becomes 4, and hence all the outputs of the red quadruple in the second layer should be also all ones, and hence in particular this orange cell will become 1. And in general, so these are all cells to which I have access on this input. And it is important to note that if we consider the last column, and if our network sorts all input correctly, this means that we have access to exactly one cell on each input, namely to the topmost cell with 0, just because the last column should be always sorted, so it has to have first some zeros and then some ones. We'll also need a lemma called accessibility. So it says the following: if we have an access to some cell C, some input X, and then we switch some input, and then suppose that we switch some input bit from 0 to 1. Well, the first possibility is that C can become 1, and then by definition we lose access to it, because we only have access to cells with zeros. Now, and the statement of the lemma is that if C is still equal to 0, then we still have access to it. And this is just a monotonicity argument. So if we know that before we made the switch, we had access to C through some input bit, right? And then we changed some other input bit because C didn't become 0. And this means that we still have access to C through the same input bit as before. So after changing this, the same input bit as before to 1, C becomes 1 because we also some other bit became equal to 1. And it can only help to become 1. As an illustration of our technique, I'll show you how to establish our lower bound for arbitrary d, which says that k should be at least n over 2 to the 1 divided by d over 2 rounded up. So basically, it's 2 over d. And in terms, we can rewrite this lower bound, and this will be now more or less d. It will state more or less that d should be at least 2 times log n base k. And recall that for k equals 2, the same lower bound with coefficient 2 was a consequence of a simple information theoretic argument. And now let's try it in that case and see. And we will see that actually now it won't give us 2 here, at least for large k. So why is that? So let's try that. So we can consider a stronger model than networks, and the model where you can just ask, you can indicate any k tuple of stones if we are in the framework of stones, and then the oracle gives you their ordering. So it's kind of a general comparison based algorithm, but for k larger than 2. So, and obviously, and in the end, we want to know the ordering of all the n stones, but there are if n factorial possible orderings, and each query basically has k factorial different results, which shows that the depth of the tree, if you consider like your algorithm in this model as a tree, should have depth at least log n factorial base k factorial, which is basically log n factorial divided by log k factorial. And now if we represent it as a network, at each layer, we do at most n over k queries. So we obtain that as before, we must have at least log n factorial divided by log k factorial, and all this divided by n over k layers. But if n and k are sufficiently large, what happens? So log n factorial is basically n log n, and log k factorial is basically k log k. So n and k cancel out, you obtain log n divided by log k, and it's just log n base k, but without any coefficient 2. So to obtain a lower bound with coefficient 2, in that case, we have to do something else, and actually access stability helps. So here is an argument with access stability. So we have to show this inequality, and we assume for simplicity that d is even, and we assume for contradiction that k to the d over 2 is smaller than n over 2. And then our network has d layers, and let's consider the middle of our network, that is a column of cells after the first d over 2 layers and equivalently before the last d over 2 layers. And then let's put first all zeros as inputs, and then let's consider the column in the middle. And on the input of all zeros, we have some access to one of the cells of this column, because, well, if we just if we just flip any bit from 0 to 1, then one of the cells in the column in the middle also changes from 0 to 1. So let's fix this cell and let it be an orange cell. So now what is drawn here? I observe that this orange cell depends on at most n over 2, in fact, on less than n over 2 input cells, because there are d over 2 layers between this orange node and input cells, and every cell depends on at most k cells from the previous column. Namely, these are these are cells from the k tuples, from the corresponding k tuple. And if we do go backwards for d over 2 layers, then instead of k, we will have at most k over d over 2 cells on which our orange cell may depend. And by our assumption, this number is smaller than n over 2. Now, what else we can notice that by the same argument, at fewer than n over 2 output cells may depend on the value of the orange cell as well, meaning that for the rest of the output cells, their value cannot change if we change the value of the orange cell. So what we are starting to do? So we start flipping input bits from 0 to 1 by 1. But we do not touch these input cells on which our orange cell may depend. So we only flip the rest of the input cells, and there are more than n over 2 of them. And so when we do this, what happens in the last column? It should be correctly ordered, right? So it just happens that each time we take, you see, the topmost 0 and change it to 1. Now, in this way, we flip more than n over 2 cells, and it means that at some moment, some cell which is independent on the orange, some output cell which is independent of the value of the orange cell becomes 1. But why? But this is actually a contradiction. Why is this impossible? So during the whole process, first note that the value of the orange cell remains 0, because we do not change, we only change cells that do not which are not connected to this orange cell. And then let's consider the moment when we have this first red one appearing outside the cells, the set of cells on which may depend on the orange cell. But still, at this very moment, we have access to the orange cell because it's still 0. We had an access to it in the beginning, and then by access stability, we still have an access to it. This means that we can change this, something that also this orange cell changes to 1, but then still the same red 1 should appear because the output column should be ordered. But the point is that since this red 1 is out of the set, which may depend on this orange cell, it cannot become, it cannot flip from 0 to 1 if the only thing which changes in the middle column is the orange cell. So we obtain a contradiction. So this is it, and I have shown you the details of the proof of our lower bound for arbitrary D and some additional details for D equals 2, 3, and 4 can be found in the paper. But anyway, thanks for watching.